So how do you teach a computer to follow one specific person in a crowded street, or a single car in the middle of rush hour traffic? This is the core challenge of object tracking, and it's absolutely critical for things like self-driving cars. But for years, the entire field was kind of stuck on this one fundamental, really frustrating problem.
And here was the problem. It was this annoying trade-off. When it came to tracking a bunch of objects at once, you could have an algorithm that was incredibly accurate but super slow. Or you could have one that was fast enough for the real world, but it made a ton of mistakes. You just couldn't have both.
And look, this wasn't just some academic puzzle. Think about a self-driving car. It needs to make split-second decisions. A tracker that's too slow is totally useless, no matter how accurate it is. As the researchers behind the paper we're talking about today put it, the speed of most accurate trackers is considered too slow for real-time applications. You are basically forced to compromise.
So what did people do? Well, the conventional wisdom was just to throw more and more complexity at the problem. Researchers were building these incredibly elaborate systems, with sophisticated appearance models to tell objects apart, and all this convoluted logic just to handle cases where one car passes in front of another. And the result? Trackers that were powerful, for sure, but just way too slow and resource-hungry to be practical.
But then, back in 2016, a paper came along with a completely different philosophy. Instead of adding more complexity, they decided to take it away.
The whole spirit behind their paper was just fascinating. The authors essentially asked, what if everyone is overthinking this? They decided to apply Occam's razor, the principle that the simplest solution is often the best one. They completely ignored things like appearance features and focused only on the absolute basics.
And this led them to a brilliant insight. What if the complex tracking algorithms weren't the problem at all? What if the real bottleneck, the thing holding everything back, was simply how well the computer could detect the objects in the first place? They had a hunch that detection quality could be holding back the other trackers.
And this is what they built. It's called SORT, Simple Online and Real-Time Tracking. The idea was beautifully pragmatic. Just strip away all the complex, slow parts of tracking, and instead, pair a brand new, powerful object detector with some of the most classic, time-tested, and efficient tracking algorithms that have ever been made.
So how'd they pull this off? Well, the elegance is really in its simplicity. It all breaks down into just 3 core steps.
It's really just a simple 3-step recipe. First, in every single frame of video, you use a top-of-the-line detector to find every object. Second, for every object you're already tracking, you use a basic motion model to predict where it's going to be in the next frame. And third, you just match them up. You associate the new detections with your predicted locations. That's literally it.
And this right here brilliantly illustrates their philosophy. Look at this toolkit. For motion prediction, they use the Kalman filter, a workhorse algorithm from 1960. For matching detections to tracks, they use the Hungarian algorithm from 1955. These are foundational, rock-solid methods. The secret weapon wasn't some new tracking trick. It was leveraging a modern, incredibly powerful detector called faster RCNN, which uses a type of AI called a convolutional neural network.
But of course, the big question is, did this beautifully simple idea actually work? Well, the data tells the whole story.
Okay, this table is the real aha moment from the paper. On the right, you see a score called MOTA, which stands for Multiple Object Tracking Accuracy. Basically, the higher the number, the better it is. Now look what happens. When they paired their simple sort tracker with an older detector called ACF, the accuracy was a pretty weak 15.1. But when they just swapped in the new powerful detector, FRR-CNN, the accuracy more than doubled to 34. And to prove it wasn't a fluke, they did the same thing with another tracker, MDP. Just by giving it a better detector, its accuracy jumped from 24 all the way to 33.5. This was the proof. The detector was the key all along.
And what about speed? Well, because the tracking part of the algorithm was so simple, using those classic, super efficient methods, it ran at a blistering 260 Hz.
To put that number in perspective for you, that is 260 frames per second. The paper states this was over 20 times faster than other state-of-the-art trackers. It wasn't just a little bit faster. It was in a completely different league.
And this is the final scorecard. On a chart like this, your goal is to be in the top right corner, high accuracy and high speed. For years, the best trackers like MD and TDOM were accurate, sure, but they were incredibly slow, running at around 1 to 10 Hz. But just look where SORT lands.
It achieves the best accuracy on the chart while running at a staggering 260 Hz. It's in a class of its own. It proved you no longer had to choose. It completely shattered the trade-off.
So what's the big takeaway here? I mean, why did this radical bet on simplicity pay off so spectacularly?
The legacy of SORT is just huge. First, it proved with cold, hard data that the single most important factor for good tracking was having a great detector. It totally changed where researchers focus their energy. Second, it created a new baseline. After SORT, any new tracker had to be both fast and accurate to even be taken seriously. But I think most importantly, it was this powerful lesson in problem solving. Instead of adding complexity to fix symptoms, like mistracks, it focused on solving the root cause, those poor detections. And because it was so simple and effective, it became the foundation that countless other tracking algorithms have been built on ever since.
And that really leaves us with a final thought. The story of SORT isn't just about computer vision. It's about a way of thinking. So what's a complex, tangled problem in your life or your work, where maybe, just maybe, everyone is fighting the symptoms instead of fixing the one simple thing that could change everything?